like to begin by thanking the organizers. It's flattering to think that I have something worthwhile to contribute to this conference. This talk might be a bit of an amuse-bouche, because whereas a lot of the other talks have focused on some, at least from my point of view, hardcore symmetric tensor categories, this will be, from my point of view, a little more down to earth. To paraphrase that national hero, Forrest Gump, I am not a smart man, but I know what vector superspaces are. So maybe that's the most complicated symmetric tensor category that will be behind the scenes here. But looking at sort of connections to finite supergroup schemes in positive characteristic. And also I've heard the phrase polynomial functors thrown around a number of times, maybe not in the talk per se, but in the audience. And I will give at least my definition of polynomial superfunctors, following the definition of strict polynomial functors that Friedlander and Suslin gave back in 1997. So what I'd like to do, some people may have heard parts of this story before, but any good yarn deserves to be repeated. So I'm going to talk about the motivation for this problem coming from the cohomology of finite supergroup schemes. I'll talk a little bit about what strict polynomial superfunctors are and some examples of them and some very basic properties. I'll talk about how they're used to prove finite generation of cohomology for finite supergroup schemes. I'll talk a little bit about how they're used. And this rhymes with the classical story for ordinary finite group schemes. I'll talk about some other directions of some questions you could ask related to those topics. And then at the end of the talk, I'll talk about some of the most recent things that John Cuiava and I looked at, looking at these super versions of these complexes of injective objects that were originally constructed by Troche, and some calculations that can be done with the aid of those complexes. So a couple of references. These are on the archive. The first two papers are paper I wrote, and then paper wrote with John that sort of cover the polynomial superfunctor business. And then John and I have a survey article on support theories for Lie superalgebras characteristic 0, and which Vera was referring to, and also positive characteristic, which should come out this year, I hope, in a proceedings volume. Okay, so what's the motivation for this problem? So if we have a finite supergroup scheme, and you could assume the field is algebraically closed or perfect to maybe make some details easier. But finite supergroup scheme over a field of odd characteristic, what can you say about the cohomology ring? Is that a finitely generated K superalgebra? And if you're interested in more complicated symmetric tensor categories, as we go through the talk, you can use your imagination to think about how might some of these results and methods potentially generalize to your favorite category. So that you can reduce this question a little bit. For a finite supergroup scheme over a field, over a perfect field, maybe I need that hypothesis, you can decompose it into a semi-direct product. So it decomposes, the normal subgroup is an infinitesimal finite supergroup scheme, and then the quotient is an étal ordinary finite group scheme. So up to some field extension, that just corresponds to an ordinary finite group. Cohomology of those is fairly well understood. To say that G0 is infinitesimal means that its coordinate algebra is a local ring, and it's going to be filtered by the infinitesimal Frobenius kernels.
So this is semi-direct product, but with a Tuka cycle possibly, yes?
I think it's just a semi-direct product. Yeah, so there's G0 will be a normal subgroup, and the quotient will be this, and it'll split like this.
Perfect.
Perfect, yeah. So extend scalars if you need to. And sitting down at the bottom of this chain of Frobenius kernels, the first Frobenius kernel, this corresponds, the representation theory of the first Frobenius kernel corresponds to the representation theory of the restricted Lie superalgebra. And in fact, if you take the dual of the coordinate algebra, you get the group ring of that finite group scheme, and that literally will be isomorphic to a restricted enveloping algebra. So in this story, the hard part of proving finite generation of cohomology is really proving it for the infinitesimal part. And then there's an argument, basically rip off from Friedlander and Suslin, to deal with when you tack on that ordinary finite group. So the hard part is the infinitesimal, and you can kind of imagine maybe you might argue by induction, starting down there with the first Frobenius kernel. So let's start the story there. And actually, let's start by thinking about an ordinary, non-super restricted Lie algebra and what's going on in that situation. So you can take your restricted enveloping algebra and you can filter it by monomial length. Fix a basis, x1 through xm. These form a set of generators for your algebra. Filter by monomial length. And then you can take the associated graded algebra. The associated graded will look like the restricted enveloping algebra of an abelian restricted Lie algebra with trivial restriction map. So it just looks like a truncated polynomial ring. And the cohomology of a truncated polynomial ring is very well known. It's a polynomial ring actually generated in degree 2, tensor and exterior algebra. And so when you have a filtration like this, it gives rise to a spectral sequence. Frequently called the May spectral sequence. May did this either in his thesis or in one of his very first papers. It gives rise to a spectral sequence. The E0 page is just the cohomology of that associated graded algebra. And then if you index things nicely, I think Friedlander and Partial indexed things nicely, the E2 page looks like this. So it looks like a polynomial ring tensor, the ordinary Lie algebra cohomology. So this would be ordinary Lie algebra cohomology in positive characteristic, not the cohomology of the restricted Lie algebra. And if you index it a certain way, the things with the x-coordinate odd or 0. So this ordinary Lie algebra cohomology is finite dimensional, or the ordinary enveloping algebra has finite global dimension equal to the dimension of the Lie algebra. And so this E2 page is finite over that polynomial ring. And by general abstract nonsense, if your E2 page of a first quadrant spectral sequence is finite over a nice subalgebra, and this is a subalgebra of permanent cycles because it's concentrated on the x-axis. So every differential just kills it because there's nowhere for it to go. If you're finite over a subalgebra of permanent cycles, it implies that the limit of the spectral sequence will also be finite over some nice polynomial subalgebra, or the image of a polynomial subalgebra. So you get this nice map that I don't know if Friedlander and Partial or maybe Janssen were one of the first ones to study it. But you get that it's a finite over the image of this map. Okay, so this is the non-super case, very classical. What happens if we look at a restricted Lie superalgebra? So now things get more complicated because your Lie superalgebra potentially has an odd part. And so when you take the associated graded, you get this exterior algebra tacked on. You have the y1 through yn. This could be a basis for the odd part of your restricted Lie superalgebra. When I take the associated graded, well, if I have an odd element and I bracket it with itself, that's equal to an even element, but that's a monomial of shorter length. And in the associated graded algebra, this just turns into an exterior algebra. And the cohomology of an exterior algebra is a polynomial ring. So you end up in the E0 page here, you still get this ordinary exterior algebra that was coming from the cohomology of the classical part, but then we also get tacked on this polynomial ring, ordinary polynomial ring, symmetric algebra on G1 star. So this is the super exterior algebra. So in the super exterior algebra, if you commute two things, x times y, normally in an exterior algebra, x times y would be minus y times x, but in the super world, when things of odd parity move past each other, you get an extra minus sign. So odd things anti-commute, so they ordinary commute, and you get this ordinary polynomial ring. And this creates a complication because this extra polynomial, the E2 page now is going to be finite over the sort of classical polynomial part, and also, well, when you put it together with this symmetric algebra on G1 star, But the problem now is that this extra polynomial part, or maybe its image, because what you really need to do is take pth powers of the generators in this polynomial part. Its image in the Lie superalgebra cohomology, it's not concentrated on the x-axis. Part of it's on the y-axis. So who knows what happens there? There are lots of potential places where the differentials could go. Does it consist of permanent cycles? Who knows? So this makes it, even for restricted Lie superalgebras, immediately harder to try to adapt classical techniques. So it's not at all clear at the outset if the image of this map consists of permanent cycles. And so it's harder to figure out what to do here. OK, so the general problem for an arbitrary infinitesimal group would be to try to cook up some nice subalgebra of cohomology classes over which the full ring is finite. That's what you're trying to do to prove finite generation. Yes?
So are those permanent cycles?
It turns out yes. To ruin the story. No.
Oh, sorry.
No, it does turn out that they are, that those pth powers. So you get some extra stuff now, and it's not totally even, but in cohomology degree p. OK, so strict polynomial functors, these come in very similar to the classical theory to try to cook up those, beg your pardon? Oh, classical,
30 years.
the non-super theory. I think, was it you or maybe Brian Parshall said anything that's published in a book is now classical. So I don't know if there's been a book
No,
that
you
has
have
this
to
in
write
it yet.
it. You have to write it.
Somebody has to write the book. OK, so strict polynomial functors were introduced by Friedlander and Suslin precisely to try to cook up these classes over which the cohomology rings would be finite. So let's start off maybe with classical polynomial functors. So maybe classically, a polynomial functor would be a functor on the category of, let's say, finite dimensional vector spaces whose action on morphisms is described by a polynomial map. So for example, let's take the second symmetric power, and let's let U and V both be little two-dimensional vector spaces. So the second symmetric power of V and the second symmetric power of W have these nice little degree 2 homogeneous polynomials as bases. And if I have a little linear map from V to W given by this matrix, you can compute the associated matrix with respect to these two ordered bases on the second symmetric power. It looks like this. And so what do you notice about the entries in this matrix?
Polynomials.
Beg your pardon?
They're polynomials.
They're all polynomials, and what specifically?
Homogeneous of degree 2.
They're all homogeneous of degree 2. Yes. So this should be a degree 2 homogeneous polynomial functor. OK. Now let's look at another example, and just to make life easier, let's work over the field characteristic 2. And let's look at the Frobenius twist functor. And classically, you can identify the Frobenius twist of a vector space with a certain subspace of degree p, in this case, degree 2 polynomials, just obtained by taking the image of the pth power map. But now, if I have that same linear map from before, and I look at the induced linear map between the image of the Frobenius twist of V and the image of the Frobenius twist of W, well, first I would calculate that this would be the matrix for the induced linear map. But over a field of characteristic 2, every element squares to itself. So maybe you would say that all the entries here are homogeneous degree 2 polynomial in the original coefficients. I would say they're all homogeneous degree 1. And I guess we're both right. So there is no unique polynomial here that's describing what's happening to the entries. So in this case, maybe you would end up concluding that the Frobenius twist functor is or is isomorphic to the identity, which maybe we don't really want it to be. So the idea of strict polynomial functors is to try to address this ambiguity. The moral of the story maybe is don't judge a polynomial function by the underlying map on sets.
But if we worked on algebraically closed field, this would not be a problem. So
No.
Why do we need to worry about finite fields?
Because I think the original motivation was Friedlander and Suslin that you wanted to do things over finite fields, do calculations over finite fields. So this is specifically designed so that you don't have to work over infinite fields.
But to prove the theorem that you prove, you don't need to.
We view these things as, like, it's the difference between, you take say an algebraic group and you think of it as its k values, or you think of it as a functor.
Mm-hmm.
And thinking of it as a functor is much more refined. And that's what these strict functions are. Exactly.
So the way that we address this ambiguity is we require that fixed polynomials be built into the definition of the functor. And one way of doing that is by changing the domain category, by twisting up the domain category so that your functors, so it's sort of intrinsic that there's an underlying polynomial. So introduce this category gamma d of v. So now I'm going to let this bold, so in my talk, my papers, boldface usually denotes a super version of some classical object. Although with this font in Beamer, it may not always be so easy to tell whether it's been bold-faced or not. But bold V will be the category of finite-dimensional k-vector superspaces with arbitrary linear maps between them. Given a vector superspace, the symmetric group is going to act on V tensor D by signed place permutations. So here's the signs of the super theory coming in. So when two symbols move past each other, if two odd things move past each other, you get an extra minus sign. And then gamma d of v is going to be the invariance for the action of the symmetric group on tensor space. If V was an ordinary non-super vector space or a purely even superspace, this would be the classical space of divided power functor. So gamma d of v is going to be the category whose objects are the same as those in script V, but in which the spaces of morphisms are given by the gamma d of the linear maps from V to W. And this identifies with symmetric group homomorphisms, albeit with this signed action from V tensor D to W tensor D. And then if you look at it this way, composition is just composition of symmetric group homomorphisms. So this is going to be our domain category. And then in 2013, Axtell defined the category, he called them, he didn't exactly call them strict polynomial superfunctors. He called them something a little bit different. But following the construction of Pirashvili, Axtell defined the category of degree D homogeneous strict polynomial superfunctors to be the category of even linear functors from this category gamma d of v into the category V. So even linear meaning that for each pair of objects V and W in the category of vector superspaces, the induced map would be an even linear map. So it would preserve superdegree. So this gamma d of the Hom space, this is bigger than the classical part because it contains not just the ordinary invariant tensors that you're used to, but it also, you have to deal with odd linear maps. So it's bigger than you might expect. And if phi from V to W is an even linear map, I can tensor that map with itself d times and get an honest invariant element in this space. So every strict polynomial superfunctor is going to restrict to an ordinary functor, but on the underlying even subcategory of script V. So the underlying even subcategory is the category where you only allow the even linear maps, the super degree preserving maps.
So this is a category is enriched over superspaces, yes?
Yes. So maybe this sort of, you can sort of see, oh, if I had an invertible linear map from V to itself, this would give me a way of having that invertible linear map act on F of V. And so maybe you can begin to see how you might get the action of a group on the image of one of these functors. Okay, and so the connection to polynomial rings, so the supersymmetric space, SD, it's defined in the usual way as the co-invariance. It's a quotient of tensor space. And we're requiring that for each pair of vector spaces V and W, that F VW has to be an even element in the space of linear maps. And then if you trace through a bunch of standard isomorphisms like if you take invariance and then a dual, that's isomorphic to taking a dual and then co-invariance and then moving things around. This corresponds to what should be the space of polynomial maps from A to B. Except in the superworld, this is also a little bit bigger than you would expect because there'll be some odd stuff in here that you wouldn't see in the classical case. Okay. So what are some examples of strict polynomial functors? There's the parity change functor that takes a vector superspace and just interchanges the even and the odd parts. If R is greater than or equal to 1, you have a Frobenius twist functor, which just takes your vector superspace and does the ordinary Frobenius twist on that vector space. We have the gamma D functor, which is the symmetric tensors. And over here, if we add together, take the direct sum over all values of D, we get this full space, this algebra of divided powers. And here we can see why it's bigger than what we would expect it to be. If I had a purely even vector superspace, it would just be the usual divided power algebra on V0. But if you have an odd part, you end up tacking on this exterior algebra.
I have a quick question. So this, how does the strict polynomial superfunctors from new to new and new even to new even, is that just like something where you tack on the parity functor, or is there a lot more?
The functors from
New to new as well as like new even to new. Is that just like all, is that?
So I mean I don't have to break up the category V into like things with even vector spaces, and odd vector spaces, sort of treat everything all at once. And so I'm allowing these Hom spaces to include arbitrary linear maps. And so my functor is required to be able to act on any symmetric tensor in there. You know, things involving both maybe even and odd stuff. I don't know if that answers your question, but.
So you have for some functors, you have two definitions here. They're equivalent, yes?
Which ones?
Like AD, there are two ADs and two wedge Ds.
Well, they're different. A would be, so this would. This
No, but A occurs twice, and also wedge occurs twice. So there are two different definitions. Yes?
Oh, well, this is an isomorphism.
Yeah, right.
Ah, okay,
Different.
okay.
So A here would be
Okay.
sort of super or signed alternating tensors, and it turns out that this is isomorphic to a gamma functor, but pre-composed with this Hom from a one-dimensional purely odd superspace. So in the superworld, in the classical world, exterior algebra, you can think of it both as a quotient of tensor space and as a subspace of tensor space. But in the superworld, these are two different things. And you can see that on the right because you can tell the difference by what do they do on a purely odd vector space. The super exterior algebra turns it into an ordinary symmetric algebra, and this A of V turns it into a divided power algebra.
And IR is Frobenius.
Yes. And then similarly, the symmetric power functor and the exterior power functor are, well, they're either even isomorphic or odd isomorphic when you sort of pre-compose with this tensor thing. And there's also a duality. And so just like in the classical case, gamma D is isomorphic to the dual of, or SD is isomorphic to the dual of gamma D. In the classical world, exterior powers would be self-dual. In the super world, lambda D is isomorphic to the dual of AD. And so what's a non-example? So a non-example would be to just take a vector superspace and project onto either the even or the odd part. And this is not a strict polynomial. Maybe this would be a degree 1 functor, but this is not compatible with the composition of odd linear maps. So like here I have a one-dimensional purely even and a one-dimensional purely odd, and there's an odd isomorphism between them. And then if I go all the way across the top, it's the identity. But if I project down onto just the even parts of the subspaces, there's no way I'm going to get the identity map through the bottom. But when you twist by the Frobenius, you do get a decomposition, and the reason is because of the definition of how the Frobenius twist functor acts on morphisms. It kills off all of the odd linear maps, or anything that involved any odd stuff in that divided power algebra. So then it really does factor through, because you don't have to worry about this kind of situation. And then this category, the projective objects, are basically a gamma D functor precomposed with POM from your favorite vector superspace into blank. And the symmetric powers are injective. And the Yoneda lemma gives you these identifications. And this is maybe how you would prove that these are projective or injective. And
Just to be clear, like implicitly you're saying that this is a dealing category of polynomial functors.
Well,
you might have to restrict to the underlying even subcategories. If you use even, linear transformations break up into even and odd parts. And if you restrict to the underlying even subcategory, then yeah. And maybe that's important for defining how exactly you compute cohomology. So these gamma, and it turns out also these A's are also projective. And the symmetric powers and the exterior powers are all injective.
What do you mean by projective and injective if you're not dealing?
Okay, in the even subcategory where you only allow even natural transformations, these are projective or injective. Okay, and then maybe the last general thing I'll say about functors before moving on to the applications is, so you can define the Schur superalgebra to be the endomorphism ring of tensor space for a vector superspace V, endomorphisms for the symmetric group action. And this, depending on how you define things, this could be true by definition. This corresponds to the category of degree D polynomial representations of a general linear supergroup. And Axtell proved that if you evaluate on a large enough vector superspace, this actually gives an equivalence between the category of strict polynomial functors of degree D and a Schur superalgebra. And this is exactly analogous to a theorem of Friedlander and Suslin. Okay, so applications both to and from finite supergroup schemes. So a couple of results. The main point of introducing all this was to try to apply it to study the cohomology of finite supergroups. But to fully understand some cohomology calculations in this functor category, we also needed to go the other way and sort of look at how things restrict to finite supergroups to deduce relations in the functor category. So the fundamental calculation is the calculation of the Ext-algebra of the Frobenius twist functor. And the direct sum decomposition of the identity, Frobenius twist of the identity into these even and odd parts gives you this matrix ring decomposition. And it turns out that the diagonal parts are both one-dimensional, purely even spaces in every even cohomology degree. And then the off-diagonal parts are one-dimensional, purely even vector spaces in all odd degrees starting in degree p to the r. And I'll sort of indicate a little bit later one way that you could calculate these things. But the point is, you can, along the way to calculating that vector space structure, you can figure out that this algebra is generated by certain extension classes that live in certain even degrees, and here are some that live in degree p to the r. So these are the new purely super phenomena that show up.
And so in the classical story, you could consider extensions of Frobenius functor with itself, and
Yes.
this is k in every degree, or what is it?
It would be one-dimensional in even degrees less than 2 times p to the r. So it would stop. So it's a well-known fact. I know it's well-known because it's on the Wikipedia page. Schur algebras have finite global dimension. Classical strict polynomial functors correspond to the representations of Schur algebras. So there you would expect the cohomology to quit at some finite point. And here it doesn't. Schur
Here it is
superalgebras
in every
don't.
even degree and every what?
All odd degrees starting at some point.
Starting, okay.
So do you construct explicit extensions the way we did?
Maybe for r equals 1 and in some small cases. But I'll actually get to this a little bit in the next 15 minutes. So maybe one of the points is part of the calculation is showing that these classes restrict non-trivially down to Frobenius kernels of the general linear supergroup. So if I take, if I have some cohomology here, I can evaluate on a vector superspace, and I can use this to get some cohomology it lands in the cohomology of a Frobenius kernel, where I can restrict down to the Frobenius kernel. But the Frobenius kernel acts trivially on a Frobenius twist, so this Hom space floats out, and this just corresponds to the Lie algebra of GLMN. And then this corresponds by standard isomorphism to some linear map from this Lie algebra into the cohomology ring. So you take all these classes, they correspond to certain linear maps, and when you paste them all together, you get this, extend multiplicatively, you get this big homomorphism from some tensor product of polynomial rings. The numbers in square brackets indicate what cohomology degree that generating subspace is placed. And you get a map into the cohomology of Frobenius kernel of a general linear group. And the big...
Can I ask this, like, if you look at this Ext algebra, is it kind of like you have in every even degree an element? So is it like all elements are powers of the first one, or?
I'll write down the algebra relations in a second. And so the point is, if you have any infinitesimal can be embedded as a closed subgroup of one of these Frobenius kernels. And so if you take this map and then restrict further to your favorite cohomology of your favorite subgroup, you can prove that it's finite over the image of this map. And then there's some other little argument to deal with what if you have that extra étal group piece. But that part's not hard. Question? Okay.
So these are the stable classes, these things that we...
Yeah, I guess this would be cohomology for the Schur. Now, I don't have a slide for this, but in the super world, cohomology for the Schur algebra is not the same as rational cohomology for GLMN. Like in the classical world, polynomial Ext in the polynomial category for GLN is the same as Ext in the category of all rational cohomology for GLN, and that's not true in the super case. So, but nevertheless, it gives you something, the image.
So is it accurate to say that you have all these polynomial functors, but really in this calculation you're only using a few of the polynomial functors? Here you have IR, but then you also have your...
Well, all the different multilinear ones that I had in the list of examples in the 2016 calculation, they all show up in there someplace. Because the original calculation showing that these things exist and the restriction is non-trivial, it exactly mirrors the Friedlander and Suslin approach based on using hypercohomology and de Rham-Kozel complexes, and this multilinear stuff shows up there. So I would say they're used. It just doesn't show up in the answer. So it turns out you would also like to understand what is the actual algebra structure of this Ext algebra. And for that, to fully nail down all the structure constants, at least for R strictly bigger than 1, the only way I know how to do that is actually to look at how do these things restrict to some nice finite supergroups and deduce the relations down there. And the real key thing is the pth power of this E sub R. You need to show that that's non-zero. In the purely even classical case, all of these E's, their pth powers are 0. In the super case, this one, it's not. So you can write down the relations, and here they are, and maybe this is maybe the most interesting one. So this basically this Ext algebra is it's more or less generated by sort of these things, and then the rest of it is nilpotent. Okay. And then the reason you would want to know exactly what those algebra relations are is because if you reinterpret it back from that algebra homomorphism, from that big tensor product of polynomial rings, you can show that those algebra relations imply that your map to the cohomology of GLMNR factors through a quotient. And John Cueva and I calculated this, and it turns out it looks like some kind of commuting variety. So if my odd part is 0, this exactly looks like things that Suslin, Friedlander, and Bendel calculated for ordinary finite group schemes. And what John Cueva and I proved was that, at least for GLMN, for, maybe there ought to be a GLMNR here, but that this induces a finite surjective morphism of varieties. So in general, for arbitrary height of infinitesimal group schemes, we don't know what the cohomology, what the spectrum of the cohomology looks like, but in height 1, so if we have a first Frobenius kernel, we're able to like push this down so that instead of things living in GLMN, it actually lives in the Lie algebra of your height 1 thing.
You don't want an R there, right? It's just putting stuff in the...
Yeah, okay, yeah, you're right. I don't want an R, because the R is built into the C sub R.
You don't want an R where?
There's an R.
I don't want a little R here for a Frobenius kernel, because the R is already here.
Commuting R controls.
So there is no, so it's correct, yes?
Yeah, no,
Yes.
okay.
Can I quickly ask a question?
Go ahead.
So in the theory of pi points, when you do it for supergroups, instead of k of x over x to the p, they take this ring k of beta alpha, where beta squared equals to alpha to the p.
Yes.
So is it related to the fact that this ring appears here?
Was inspired by that.
I think there's definitely a connection.
But probably it's more than that. Probably there is a reason. Yes, why they both appear.
The strongest theorems are for unipotent finite supergroups, and maybe John will talk about this some more later. So what are some other directions? So sort of a curious byproduct of those calculations is apparently if you look at rational cohomology for the general linear supergroup, the second rational Ext-group is non-zero. And this is curious because in the ordinary cohomology of GLN, all the higher cohomology vanishes due to Kempf vanishing, for example. So a problem, which I don't really have any idea how you should fruitfully begin to try to do this, but might be to calculate what is the rational cohomology ring of GLMN. You know, Eric was talking about trying to develop support theory for non-finite algebraic groups. Maybe in the super case there's some kind of support theory. Maybe it's not very big, but maybe it tells you something representation theoretic. For m equals n equals 1, you can calculate this because GL11 is solvable, and the layers are pretty simple. And it appears to be just a polynomial ring generated in degree 2. So maybe there's some kind of rinky-dink support theory there. I don't know what it tells you. And then you could go even further. There's algebraic supergroup Q of n, for which Brunnen and Kleshev calculated that the Ext1 is a one-dimensional purely odd superspace. So you could also ask, what's the rational cohomology ring there? Those Q of n is connected to a type 2 superfunctors that Axtell defined, connected to a type Q Schur superalgebra. And then John's former PhD student, Joey Randich, he defined some even more general polynomial functors that are connected to the generalized Schur algebras or Schur superalgebras defined by Kleshev and Muth, I think. Anyway, there are more general functor categories, and they could be relevant for calculations.
So this is even in characteristic 0, right?
This is positive characteristic, odd characteristic.
But the X2 should not depend on characteristics.
I don't know.
So this Ext1 for Q, if you take SQL, it disappears, right?
I don't know.
Okay.
Maybe I don't. All I know is I can point to the lemma in their paper that says that. And then maybe this is getting into what I'll talk about in the last 8 minutes or so. If I have an ordinary non-super strict polynomial functor, there's no obvious way that can be lifted to the structure of a strict polynomial superfunctor. The problem is a non-superfunctor a priori doesn't know what to do on the full morphism space, because the full morphism space, if I'm taking this gamma of Hom VW, it includes not just the classical symmetric tensors on the even subspace of linear maps, but it includes an exterior algebra part. And the classical functors aren't defined on that kind of thing. But with the Frobenius twist functor, it kills off all of the odd generators in there. And so you end up with landing in a purely even space, and then a classical functor does know what to do on that. So you can take a classical functor and compose it with one of these Frobenius twists and get a new strict polynomial superfunctor. And one of Antoine Touzé's is sort of the expert on all things with calculating cohomology for the classical strict polynomial functors. His PhD student, Giordano, just recently wrote a thesis sort of looking at these Frobenius twists of the polynomial superfunctors. And he conjectured, and this is exactly analogous to a conjecture that Touzé made and that later, I think, Chalupnik proved. Basically saying the general version is if I pre-compose with an additive functor. In the classical case, the additive functor is just our Frobenius twist functors or the identity. In the super case, you can also pre-compose with the parity change functor, or there are sums of these things.
So what does it mean, G with subscript ER? So I see definition of
W,
GW.
Yeah, this is a parameterized functor where you pre-compose with tensoring. And this ER is exactly one of these Ext-algebras that was calculated earlier. And so the conjecture is that you can relate the polynomial superfunctor cohomology to cohomology in the classical non-super category, but one of your functors has then been parameterized by an Ext-group calculated from the super category. So these Ext-groups down here, you can all sort of recover them from things that are already known.
Is both parts a conjecture, or is the first part true?
I think the thing on the right is graded by the total degree. So there's part of the degree is coming from this piece in here. I'm going to be vague about how exactly it's graded.
Is it a statement that a certain Grothendieck spectral sequence of composition of functors degenerates?
Yes, exactly. And so the way that Touzé approached this, although I'm not sure if this is how Chalupnik verified the conjecture in the end, but Touzé approached this and proved it in many cases by using a very nice injective resolutions of certain kinds of functors to get this Grothendieck spectral sequence collapsed. And so this is the stuff that John and I have worked on most recently, was looking at basically the naive generalization of these injective resolutions that had been constructed by Troche. So the general problem that you can try to do is try to construct an injective resolution in this functor category in general, of a Frobenius twist of a symmetric power, but you could even let m be equal to 1. And in Friedlander and Suslin's paper, they did this for p equals 2. So Troche came along and gave a construction that generalized it to larger primes. And so the way that Touzé presents this, the first thing we'll do is we'll start with this graded vector space. This is the letter Shah. Is that correct? Yeah. Okay. So this graded vector space, it's p-dimensional, and the degree is simply of a basis vector is simply the subscript. And I get this functor, and this functor is going to, when I plug in a vector space, so this is purely even down here at the bottom at the moment. I think this gray bar shouldn't be here. I don't know why. There's no consequence listed, so I think that was a copy-paste error. But this vector space inherits a grading in the obvious way from the fact that these basis vectors each are graded. And then I'm going to define a linear map on this vector space Shah that just kicks every basis vector up 1 degree and kicks the last one off, because there is no Shah sub p. And then I get an induced map on these symmetric powers, and it's really just the algebra derivation that's induced by this underlying map of vector spaces. And this is the story for one Frobenius twist. For higher Frobenius twists, you have to do something more complicated here. But in this case, what you don't get a complex, you get a p complex. This is a p differential. If I do this map p times, I get 0. So what you then need to do is take this p complex and contract it. And in general, there's more than one way of contracting. But what we could do is we could start the degree 0 part. We could apply d once, and then we could apply p minus 1 times, and then we could apply it once, and then p minus 1 times. And in this way, we can contract and get an honest-to-goodness complex. And Troche's theorem was that this complex is acyclic if my polynomial degree wasn't divisible by p. And if it was divisible IP, it gives you an exact, in fact, a resolution of a twisted symmetric power. And in fact, this is a finite resolution, because these things are 0 for large graded degree. So the reason these are so useful is because of a graded version of the Yoneda lemma. It just lets you, when you hom into the underlying object of these resolutions, you get this very nice description. And the consequence is that if you use one of these resolutions to compute cohomology in the classical case, it just turns into a hom calculation. And all the stuff in odd degree, based on how you regrade, is 0. So it just totally collapses, and you just read off the answer.
This is resolution as by projectives.
The symmetric powers are injective.
But the resolution of, you said the resolution.
It's a resolution of a twisted symmetric power by other symmetric powers.
Injective resolution.
The untwisted symmetric powers are injective objects. And you're resolving a twisted symmetric power. OK, I've got 20 seconds left. So John and I looked at this and we said, well, we're kind of naive because I am not a smart man, but I know what vector superspaces are. So we looked at this naively and asked, what happens when you just do the naive generalization of this? And you get something more. So maybe one of the morals of super is you get more. Maybe you didn't want more, but you're getting it. And so you have inside this complex, you have the cocycles that you had before, which were these pth powers in cohomology degree 0. A derivation is going to, in characteristic p, is going to kill a pth power. But you also get some extra stuff. And the reason something of this form, so this is sort of sitting in an exterior algebra part of this supersymmetric power. And the reason this will be a cocycle is because my differential is going to come along and it's going to sort of hit each of these factors in turn. And it's going to try to kick one of these basis vectors up to the next spot. But if I kick SHA-0 up, it'll have 2 copies with SHA-1 tensor U and an exterior algebra thing squared to 0. So you get these extra cocycles. And it turns out that sort of describes the whole picture. So you can still construct these p complexes, you can still contract them, and you can still compute what the cohomology of this complex looks like. And it does look like a twisted symmetric power, but it's sort of smeared into a bunch of high cohomology degrees. It's not all down in degree 0. So on the one hand, it's not a resolution any longer. On the other hand, the cohomology is still nice, and you can get some mileage out of it. And in particular, if you were just looking at this for when m was equal to 1, you get a complex whose cohomology is non-zero in only 2 places, and you can begin to splice these together. So John and I we did, for r equals 1, you can make this very explicit. You can construct injective resolutions of a first Frobenius twist. And this is maybe really the key case for doing any kind of calculation, especially if Giordano's conjecture is true, because then you can kind of reduce everything else down to the non-super case. So you can get actual periodic injective resolutions, and then just like in the non-super case, you can compute this cohomology just by homming into the resolution. All the odd stuff is 0, and out pops those vector space calculations. And then the last thing, and this is the last slide, you can also use this. So as an application, we sort of redid the super version of some calculations that Franju, Friedlander, Skvorchenko, and Suslin did. And the answers look the same as in the non-super case. But maybe the point is you're taking symmetric or exterior powers, but now on something infinite dimensional. All 4 of the vector spaces at the top are now infinite dimensional vector spaces, I think. So that's the end of the story.